Okay, question 1 said two tiny spheres carrying charges of a positive charge of 4 microcoulombs and a negative charge of 3 microcoulombs. They are separated by a distance of 50 millimeters. Now 1.1 said calculate the magnitude of the force between these spheres. Alright, so just going through question 1.1 of exercise 6.1 last week. So 1.1, remember they said, well, we had a positive charge of positive 4 microcoulombs, right, which you all know is equal to 4 times 10 to the minus 6 coulombs. Q2 was negative 3 microcoulombs, which is negative 3 times 10 to the power of negative 6 coulombs. Our distance, which is r, was 50 millimeters away. Okay, we need to convert that into meters, so I'm going to keep it scientific notation, 50 times 10 to the negative 3 meters. Okay, put that in the calculator, you know what that is equal to. Okay, so this might have been the example I did last week, but I'll just start it off again. We know that the electrostatic force is equal to Coulomb's constant multiplied by the product of the charges, Q1, Q2, all divided by the distance squared. Right? We pop these in our calculator. So 9 times 10 to the 9 multiplied by 4 times 10 to the negative 6 multiplied by 3 times 10 to the negative 6. Okay? Remember, we don't add the signs on the charges. We don't add them, okay, because they are only there to dictate that they are opposite charges. All over 50 times 10 to the minus 3 all squared. We get an answer of the electrostatic force to be equal to 43.2 newtons. Alright? And then the next question, they split up this answer into two questions. Asked, is the force attractive or repulsive? Now this is where our signs come in over here. So we can clearly see we've got a positive and a negative, so we know that they are opposite charges, and just like when it comes to a magnet, by intuition, opposite charges do attract. So we know it is definitely a force of attraction, so we can just write attraction as they asked us there, or we could have also written force of attraction. Either one, doesn't matter. Then we have a look here at 1.3. Asked us a question. If the distance between the spheres is halved, how will this affect the magnitude of the force? Okay, now this is a question that I need to teach you. There is a method for answering this question. Okay, there's a method, so I'm going to teach you the method. Okay, so they asked us here, how will the doubling or the halving of the distance affect the magnitude of the force? Okay, well, first of all, we know that r represents distance in the equation. So they say that r is halved. So what they're technically saying here is that r, which is invisible 1 over here, is now half r. Okay, or r over 2. Right? It's no longer 1. Okay, so let's have a look at how this will influence the force. This is how we start writing it. Okay, Q1, Q2, we use an arrow over here because we're trying to find out what factor will the force increase by over r squared. Keep our arrow going to the next line. Well, we have to substitute half r for r. So Q1, Q2, shift is for me to draw a straight line, all over half r all squared. The next line, we can see we obviously have a function or sum that we can perform. So Q1, Q2 is going to stay on top because they're just a product of the charges. But we have half r squared, so we're still going to get r squared, but what's a half squared? Alright, our half squared is quarter. Alright, so we end up with a quarter r squared. Carrying on up here, you can see that we have 1 over 4 multiplied by Q1, Q2, all over R squared. As you can see, I just removed the one that's in front of this one, and I separated the two. Right? There's a 1 there, I separated the two. Can we see that? Right? That's all I did. So all you have to do is you put this little baby, first of all, you just draw that line below, put this baby in your calculator, you'll get that that's a factor of 4. 1 over 1 over 4 is 4. So therefore, the force is going to be 4 times greater. Okay, because this is what the electrostatic force is equal to, right? Obviously including Coulomb's constant, but we don't include that now because that's a constant, that's always going to be there. But our force is going to be 4 times greater. So that's what happens when our distance is halved. And we worked it out without using almost any numbers at all. Okay, do we all understand that?
Yes.
Fantastic. Right. Let's have a look at the next question. Right. So for question 2.1. I need to. Okay. Question 2.1. They say now that the charges in 2 small insulated spheres are positive 14 microcoulombs and negative 2 microcoulombs, right? Respectively. Now it says here that the spheres are brought into contact with each other and they're separated by a distance of 100 millimeters. Calculate the force between them. Right. So, the total charge on the 2 spheres they say, are brought into contact. Okay? Formula from grade 10 tells us that the charge on the spheres after they are brought into contact, alright, is equal to the sum of charge on one of the charged objects plus the charge on the second object divided by 2. Alright? Bring those in together, so they tell us we have a positive 14 microcoulombs. I'm going to keep everything in microcoulombs, by the way, right? Plus minus 2, all divided by 2. Right? So we've got positive 14 plus 2, it's positive 14, sorry, not minus 2. 14, positive 14 plus minus 2 gives us positive 12 microcoulombs, all divided by 2. Therefore, the charge on each of the sphere, in other words, charge on 1 and 2, is going to equal to positive 6 microcoulombs. Okay? Now that I know what's the charge on each, okay, I can now go and perform my electrostatic equation, which is F is equal to K, Q1, Q2, all over R squared, equals to 9 times 10 to the 9, multiplied by positive 6, so 6 times 10 to the minus 6 coulombs. There are 2 of them, so it's multiplied by itself, so I'm going to save space and just go squared. Hope everybody sees that. All over, it's 100 millimeters, so you need to divide by 1,000, which is the same as 100 times 10 to the minus 3 squared. Pop it into your calculator. Therefore, the force should equal a 32.4, if you round it up to 1 decimal place, newtons. And this one is definitely a repulsive force because they are both positive 6. That was 2.1. Right, then we're going to go 2.2. Okay, 2.2 asked us if the magnitude of each charge is now doubled, how will the magnitude of the force be affected? Right? So now the magnitude is doubled. In other words, it's now of each of the charged objects. In other words, it's no longer 6, alright? It's no longer 6 times 10 to the negative 6, it will now obviously be 12 times 10 to the negative 6, right? It's doubled. But what they're saying here is that Q1 now becomes 2Q1. And Q2 obviously becomes 2Q2. So in other words, no longer 1, but it's 2. Alright? And it's the product of the charges, so it's Q1 times Q2. Alright? So 2 times 2, right, is definitely going to equal 4. So we can see there that definitely that the force will be 4 times greater. Right? All I did was double the charges. There's an invisible 1 in front of both of these over there. Alright, so if they are doubled, so it's obviously 2Q1, 2Q2, 2 times 2 will be 4Q1, Q2. And that's 4 over 1, the distance is kept the same, so therefore the force will be 4 times greater. That's it. Alright, does everybody understand that again? Alright, let's have a look at question 3. Okay, question 3 was just a one-part question, so there wasn't any 3.1, 3.2, it's just question 3. They tell us that the electron proton in a hydrogen atom has a separated distance of 35 picometers. Alright, picometers mean 10 to the negative 12. Right, 1 picometer is 1 times 10 to the negative 12 meters. Now calculate the force between them. Okay, well we know that the charge on an electron is negative 1.6 times 10 to the negative 19, and we know that a proton is the opposite, which is positive. So we know that because they have opposite charges, that there's definitely going to be a force of attraction between these two batteries. Alright, so again we give them a formula. F is K, Q1, Q2, all over R squared. Just make sure that our R is given by 35 times 10 to the negative 12 meters. Okay? Right? And obviously R squared will just be the squared version of that. Okay? So I'm not going to do the sub-in process for this one because I'm sure by now you know how to sub in. Alright? But I'll just write the information here that Q1 was the electron, which is negative 1.6 times 10 to the negative 19. We would omit the negative in the equation. Coulombs, Q2, which was the proton, positive 1.6 times 10 to the negative 19 coulombs. If we do that, and the force between this proton and this electron is given by 1,88 times 10 to the negative 7 newtons, and like I said, there's a force of attraction. Oh, spelled attraction wrong. Alright. Lovely. Question 4. Alright, question 4 asks us that two alpha particles are separated by a distance of 10 to the negative 10 meters. Quite small, but there is a separation between them. Again, this one, calculate the force that exists between these two particles. Okay. Again, this one is, we got to know what an alpha particle is consists of, and I think I gave that to you last week. I might not be sure, but I'll write it down here. An alpha particle, alright, is equal to 2 times 1.6 times 10 to the negative 19 coulombs, sorry. 2 times 1.6 times 10 to the negative 19 coulombs. That's an alpha particle. So there's two of these, okay? Again, in our formula, we plug them in. I'll do the subbing for this one. So the force is equal to 9 times 10 to the 9. I'm going to use brackets just to neaten the work up a little bit. Brackets 2 times use another bracket, 1.6 times 10 to the power of negative 19. There's two of them, alright? So if there's two of them, we're going to square them, okay? Because basically going to be times the same thing. All over 10 to the minus 10 all squared. The answer that we should have gotten there is rounded off to two decimal places, 9.22 times 10 to the power of minus 8 newtons. And because they are the same, there's no negative and positive on each and any one of them. They are the same, so there is a repulsive force that occurs at 4.1. Did we all get that?
JP?
What's up?
Could you just explain what's the alpha particle again? Is it the 2 times
so it's 2 times the charge on a electron or proton. It's 2 times the charge of that. So which means an alpha particle basically consists of 2 protons, right? With two neutrons.
Okay,
that's what an alpha particle is. So it's just 2 protons together. So that's why the charge on an alpha particle would be 2 times the charge on one proton. For example.
Oh.
See?
So it's just 2 times the charge.
That's it, yes.
So,
that's it, yes.
And the negative 19 is just the charge of what? What was the...
So negative 19? Negative 19 is this one. It's the charge on an electron or proton. So an alpha particle would be 2 of these.
Oh, I see. Okay.
Cool.
Now I get it.
Awesome. Okay, so just remember that. The alpha particle consists of 2 protons, right, and or 2 neutrons. So it'll be 2 times the charge on a proton, which is a positive charge, and if it is a neutron, then you know that it's a neutral. Okay, but in this case, they just say it's 2 alpha particles. Okay, I would always assume that it's just go with a proton because they're the same anyway. It's still 2 times 1.6 times 10 to the negative 19. That's why I used the bracket just to show that it's 2 times the charge on a proton or neutron. It's just 2 times that. In the textbooks, they don't seem to use the bracket system. So I put the bracket system there just to help with neatness and eliminate confusion. Footnote 2 asked us if one of the alpha particles is replaced by a proton, okay, how would this affect the magnitude of the force? So now they tell us that if one of the alpha particles is replaced by a proton, so no longer 2 protons, 2 neutrons, right? But now maybe they're replacing one of the neutrons with a proton, alright? Or they're just replacing it with 1 proton, right? So they're taking the alpha particle out and just put it in the proton. They want to know how will this affect the magnitude of a force, okay? Well, a proton, we can see 1 proton is clearly only half that of an alpha particle. If an alpha particle is double that of a proton, because it's 2 protons or 2 neutrons, then clearly 1 proton is only half. 1.6 times 10 to the 19. Alright? So since a proton has half the charge of an alpha particle, well, clearly the force will be halved. And we know this because the force is directly proportional to the product of Q1 and Q2. Alright? There's a direct relationship here. So if this happens to this side, the same will happen to that side. Questions?
None so far?
Lovely. With that being said, the last question is number 5. So number 5, Number 5 was a bit of a different question. Let's go this one. Number 5 was a question where they asked us to calculate the distance. Okay, 5.1. So 5.1, they gave us that the force was equal to, obviously, we know the product of the Coulomb's constant, 10 times 9 to the 9, multiplied, and they gave us two charges there. One was, both were positive, so it's 5 times 10 to the negative 6 coulombs, times 8 times 10 to the negative 6 coulombs, and we had R squared at the bottom. And they gave us the force to equal 400 meters. Sorry, that was the force that was given to us in the addition. 400 here. Okay, 400 over there. So what that basically means is, obviously, the top side is going to stay the same. Then we get rid of the R squared on both sides. Multiply by R squared. Then divide both sides by 400. So we're going to end up with R squared is going to equal all this. I'm going to use the quotation marks. Save right in time. So basically this means all of that divided by 400. And remember, now the distance is squared. So after we get an answer for 9 times 10 to the 9 times 5 times 10 to the negative 6 times 8 times 10 to the negative 6 divided by 400, we still need to square root our answer. Okay? We're still going to need to square root this. Okay? To get what R is going to equal. Right? Because R represents the distance, not R squared. Okay? R squared is just the distance squared. Right? Now R is the distance. We should, if we round it up to 2 decimal places, get an answer of 0.03 meters. Right? Or some decimal looking similar to that, or very close to that. Right, did we all get that? That was quite a nice question. Assume that is correct. Everybody got that question. I'm happy. The last question, 5.2, is a simple, straightforward answer. What does the fact that the force is repulsive tell you about the charges? Well, that's very basic. They are like charges. Okay, like charges repel each other. Unlike charges attract each other. That's it. Boom, bada, ba. Done. And that was the exercise. Okay? Good practice. Very good practice, in my opinion, for electrostatics section. Very good practice. We're going to move on now to electric field. Alright, so electric field is our next topic. Right, now with electric fields, okay, this forms part of electromagnetism. So this is the first part that we need to go through before we get to indeed electromagnetism and before we get to electromagnetic induction, okay, which is quite the fun part, and also that's where your practical would have come in had you guys been at school during the time of this practical. Okay, basically we use a magnet to induce a current. Alright, so it's almost like, I wouldn't say it's an alternative for electricity, alright, but it's just another way of generating electric current. Okay, so I'm sure if the magnet is quite strong, or if your apparatus regarding that is quite strong, if it was strong enough, even electromagnetic induction could possibly shock the living daylights out of you and possibly kill you. Okay, so let's go. Electric field. So what is an electric field? Okay, first of all, electric field is the space around an electrical charge. Right? Let's get that down. So first of all, it's the space around an electrical charge. Right? Next part, in which any other charge will experience a force. In which any other charge will experience, dot my I there, slide it, experience a force, last part, which is electrical in nature. Right, so if we still touch a charged object, for example, static electricity is not really current in terms of in Ohm's law, where we know that V is equal to I times R. So I, obviously, current in a circuit is measured in amperes or in amps, which we will get to after we are done electromagnetism, electromagnetic induction. Circuits is the next build-up, the next part there. So not necessarily do we experience I or amps flowing through our hands, but we rather experience an electric-like experience. In other words, if we touch current, right, or electric current, we will shock. Same way, we touch something that has been statically charged, right, and the transfer of electrons goes onto our hand, we shock as well, right? We touch a doorknob, we touch someone, you know, sometimes walking in the mall, I would often touch my mom and I would shock like crazy, right? I did it for a while and then I think my body just became used to it. So literally, I'm basically like a vicious am. Great. Okay, so that's the definition of an electric field. Very important definition, is examinable. Okay. So if we draw, right, so the first drawing that I just want to draw for you guys is a field around a positive charge. Right, a field around a positive charge. Let's say I have my positive charge, right? I'm going to draw it circularly. Okay. We want to know how's this field going to exist? How's the pattern, right, or the direction of the field going to look around a positively charged point charge? Okay. First of all, I'm just going to draw my almost what it looks like compass lines. Okay, to demonstrate. Okay, and this is also quite frequently asked in exams as well. Okay, so in this case, okay, a field around a positive charge is going to have the field lines radiating outwards. So the arrow will be going outside, right, or outward rather, okay, from the charge. Okay, so that's how it would look. That's how a field looks like in a positive field around a positive charge, the direction of the field. Okay, but now let's do the same thing. Yeah, let's use this one. Okay, so let's have a look at the field, right, around a negative charge. Okay, at minus V, obviously, negative. Okay, so just draw my circle again. It's minus. My line's going. Alright, I'm trying to rush through it. Still get effective. There we go. Somewhat looks okay. Okay, these lines are going to be going into the charge. In other words, the field direction is going to be going in towards the negative charge. Okay, so that's how those electric lines are going to look. Say we have two like charges and we want to see the field that exists between them. Okay, so in other words, I've got two like charges. Alright. Let's go to Sorry guys, I got distracted with something very small. I apologize. That might be a little too far away. Okay. So I've got 2 positive. Okay. So we know how positive is going to look like. Okay. We know we're going to have the arrows pointing outwards towards each other, right, or away from each other. Okay. So this is how we draw them. Remember, they are 2 like. Okay. So if we got, for example, like we had lines going all out and like this, and all the arrows are going out like that. So they look almost like a little beams, right? And 2 of them are coming into contact with each other. How do they look? Well, first of all, these guys at the back are going to be all normal. Okay, so they're going to be okay there and over there. Let me just fix this line up here. There we go, and there we go. But now, as we get closer and closer here to this guy, what you're going to see is diverging lines. So in other words, you're going to see this pattern start to take shape here. Okay, so you can clearly see they are diverging away from each other. Okay, same thing over here. So you'll see this pattern. So let me ask you, how do you draw 2 like charges, the field around them? This is exactly how we would draw them. Okay? Alright, so I may have a little bit more lines, just make it a little less. Okay, so this is for 2 like charges are in the same electric field, that is the field lines around them. Okay, but now what happens if you want to draw them when they are actually 2 opposite charges? Okay, let's get a different color. So now we want 2 opposites. Okay, so that's for 2 like, 2 opposite, or unlike charges. Okay, well, same, positive, one is negative, right? We had a diverge in the top one example. Now, obviously we know like charges attract each other, so we're going to have a converging style happening over here. Alright, they converge in the middle. Okay, positive. Oh, something I forgot to do here, which I'll do in yellow. Obviously, remember, the positive charge, the field lines still go outwards. Okay, they still go outwards all along the charge, the field lines. Okay, so I'm just drawing in there for everybody quickly. Sorry, I omitted them. But this is a very part of the drawing. If you get asked about it in the exam, it's quite a good exam question. Okay, and here the positive one over this side. Okay, again the same thing. These ones are still generated outwardly rather. Okay, so they will still have this one will go out, this one will go out, like that. Give them negative, okay, you got the same lines. Except that with the negative, the lines are going into the charge. Okay, so yes, you got 2 different lines over there. So that's how the field lines look for opposites and for like charges. Okay, very important that we get them down as notes. So because the example of these is called radial fields. Okay, that's how we used to demonstrate them. We call them radial fields. Okay, the field is strongest next to the charge, and thus the field lines are also the closest together. So the field line would be closer together, close to where the charge is. Okay, so the point charge could be over here. Also add another point charge, like over, depending on where the charge would be in this. Added a point charge over there. Okay, that would be the strongest part of the electric field. Okay, so this is all theory, but let's see how they work in practical with regards to calculating the strength of an electric field. So when it comes to calculating the strength, okay, most of the marks will come in under the section. Okay, first of all, we need to know what is electric field strength, or how can we define it. Electric field strength, alright, at a point. Alright, electric field strength at a point in the field electric field strength at a point in the field is the force at which a charge experiences, which a unit charge experiences at that point. Okay, so that does tell me that the formula is going to look somewhat like this. Electric field at a point in the field is the force which a unit charge experiences at that point. We can also insert the word which a unit positive charge. More specifically, okay, the charge will almost always be positive in your exam, in your test, okay, and that is given to you by the formula that E is equal to F all over Q, okay, for E standing for electric field strength. Alright, electric field strength is going to be measured in newtons per coulomb. I can understand where this comes from because force measured in newtons and Q is the charge which is measured in coulombs. Okay, it's the N times C to the minus 1. Alright, the force, F for force of the test charge, which we know is in newtons, and Q is the charge, right, or the magnitude of that charge, which we know is measured in coulombs. Okay. This is also a vector quantity. In other words, there will be direction of the electric field strength. Okay. That's why in the previous drawings there was directional arrows. Okay. Therefore, it is a vector quantity. Okay. It will be in the same direction as the direction of the force that's experienced by the positive test or positive unit charge. So if I have a little mini example here, which I will just demonstrate at the bottom here, just to explain this part. This is the first formula, by the way. There is another way that we can also calculate it. Electric field strength. Okay, but here there's no distance for this one. This is just given the force, charge, and we calculate the electric field strength. So if they tell me in my example that there's a charge that exists and it is equal to, let's see, 3 times 10 to the minus 4. Alright, coulombs that exists. Okay, it's at a point in a field where the magnitude of the field strength, so they give me N. Magnitude of him is given to me by 3 times 10 to the 7 newtons per coulomb. So it's quite a strong one. Okay, 3 times 10 to the 7, right? It's positive, it's not minus 7, right? It's to the 7, right? It's quite a strong electric field, right? They now want to know, calculate the magnitude of the force, right? That is exerted on the charge. Okay, well, in our example, E is equal to F divided by Q. Okay, they give me E, which is 3 times 10 to the 7. I don't have F, but I do have Q, which is 3 times 10 to the minus 4. So therefore F is going to equal EQ, which is 3 times 10 to the 7, brackets, times 3 times 10 to the minus 4. Therefore, after a little bit of calculator work, the force that this charge, or that is exerted on the charge, okay, is equal to 9 times 10 to the 3 newtons. Right? There's my answer. Right? I calculated the force that this charge experiences at the specific point. Okay. So this is electric field strength, the first formula. But there is another one. There's another formula. And what happens if you only want to know what the electric field strength is at a certain distance from a charge? Okay, so you want to know. Okay, now distance comes into the mix, and we can obviously apply that to our radial fields. When we have a uniform field, all right, that has a constant strength, so we would not apply it there, but we have a radial field, right, like I just the previous drawings. And now we have a distance equation that is also brought into the mix as well. So let's have a look at what happens if we want to find the field strength we want to calculate the field strength at a distance, which is obviously measured in or used to or denoted by R, from a charge, which we know is Q. Now what formula do we use? Okay, in other words, we have a charge over here, which is Q, a very bad Q, I gotta fix it up, Q, and boom, there's a certain distance over here, R is equal to however much. What's this electric field strength over here? How do we do that? Well, this is how we do it. Formula, which is formula number 2, is electric field strength is equal to Coulomb's constant, which is K, times the charge all over R squared. So Q over here stands for the point charge, which is creating the electric field. E is the electric field strength, and R is the distance between Q and the point at which E is calculated, right, which is electric field strength. Okay, so let's say, for example, here, I have an example where they say that I need to determine the electric field strength at a point, right, where the distance, at electric field strength E at a point which is 300 millimeters, right, so we have 300 millimeters, okay, which is basically 300 times 10 to the minus 3 meters, alright, from a point charge Q, which is negative 3 times 10 to the minus 4 coulombs. I need to determine the electric field strength. Well, I'm going to use this formula here. E is equal to K Q over R squared. Right? What I do here, I know that's 9 times 10 to the 9, all multiplied by minus 3 times 10 to the minus 4. Just heated that one up there a little bit. All over 300 times 10 to the minus 3. Okay, this one's a little easier because we've got zeros. So 300 times 10 to the minus 3 is basically 0.3. Okay, so I'm going to write that as 0.3 all squared. And so it's simple calculator work. Therefore, electric field strength, right, which is at a point, all right, at the specific point, is equal to 3 times 10 to the 7 newtons per coulomb. And because we get a positive answer, all right, because we know that it was a negative charge, which we actually, the same rules apply over here. If it's a negative charge or positive charge, it doesn't matter. We don't include the negative or positive in there. We just take the value of the charge. Okay, so it's just times 10 to, just 3 times 10 to the minus 4, sorry. But because we knew it was a negative charge, we know that when it's a negative charge object, the field lines go into the charge. So we would write 3 times 10 to the 7 newtons per coulomb inwards. Right? And that's how we work it. And that's the basics of finding electric field strength. Very easy, or should I say, not complicated. Right? And we're not saying very easy because we all learn at different paces. So let me just say that it's not complicated. Right? It doesn't have to be complicated at all.